All right. Good morning, everyone. This is a network steganography techniques project. First of all, I'd like to introduce the team for you. That's Manuel, that's Robert, and my name is Osama, but of course I'm not Osama bin Laden. You can call me just Sam. All right. So this project has been started last semesters in fall 2015. And I'd like just to say that we follow some methodology in this project, like we do some tests, we do some experiments, and we take our notes, we do research, and finally we come a lot of notes. But that's, as I told you, that is on a scientific and educational way. So every time that we get to a point, we move from that point to the next one as we finally want to do something with the network steganography. So actually, we got a lot of lessons learned and a lot of experience in this project. So I'm sure that most of you know the network steganography or the steganography. First of all, let me just explain something about steganography itself. It's like it's a way of hiding information in a carrier. You are hiding a secret information in a carrier. This carrier could be like a video file, like audio, or a picture. So you are hiding some information in that part, but all others parties are not concerned of what you are doing. So that's the secret. It's a little bit dangerous for the people who's gonna use that in a bad way, but that's kind of an art. So steganography is a way of concealing data, concealing secret data in the carrier. There are three ways that you can use in steganography. The first one is insertion. Like if you have an empty field and you're gonna fill it, that's called an insertion. And the second one is substitution. Like if you have a field with already existing data and you're gonna make some modification for this data, but without affecting its main meaning. And the third one is generation. What does this mean? Generation is like if you have like a text, for example, and you have a rule. So you're gonna say that I'm gonna take the first letter of each word, then finally I'm gonna do a secret thing. And that will be sending for the other part. So that's the steganography in general. Let me just deep in with the network steganography. Network steganography with the same meaning, but our carrier here is a network protocol. So network protocol, like it could be TCP, UDP, HTTP, whatever. So our carrier here is a network protocol, and the main purpose here is to send a secret message, like we call it covert message, from way to another. The steganography is like it's a deal between two parties. You can't say that I'm gonna send something from here to anyone. No, you have just to be like a deal between two parties. They have to be agreed on that before doing anything. All right. There are two techniques in network steganography. The first one is packet delay. What's the packet delay? Packet delay is like you hold the packet for a certain amount of time as a sender. Then you release that to the receiving side, and the receiving side is decoding that part. So that we call that packet delay, because you are tuning your time just for the receiver. Between sending and receiver, you are tuning your time. And the second method is modify packet contents. Modify packet contents, you know that the network layer are divided like in layers, fields. So you are making a choice for one of these fields, and you insert your data in that. But the main things that should not affecting the arrival of that packet to the receiving side. So that's the two methods, the two techniques on the network steganography. Before moving to our goal in this project, let me just say something. Just to summarize the network steganography, you are now to specify your layer, your protocol, which field you're gonna deal with, and which method that you're going to use for network steganography. So our goal here in this project is to find the best method just to use for network steganography. So if there is an existing tool, you're going to utilize that. And if you don't, maybe you need to develop one from scratch or make some modification for the existing one. So that's what our goal in this project. Next slide. Okay, what we did then? In this project, the first thing we need just to set your environment. So we prepare our testing environment between two PCs, and mainly all our tests were done from point to point. Just all our tests done from point to point, and we start doing our test. The first thing we do, we start by layer 3 and using the protocol ICMP. That's at layer 3, protocol ICMP. And the method used is called Timeshifter. This method is work in the first techniques that it's time delay, packet delay, I'm sorry. First techniques is work on packet delay and called Timeshifter. So as we said before, you hold the packet for sometimes, and you release it for the receiving side. Also, the team make a modification for Timeshifter, and they do something new called StegNet. The StegNet is also work on the ICMP packet. Bless you. The ICMP packet and at layer 3, and this one is work on packet modification contents. The most interesting part of this project is the last part, that it's about using an application called, everybody know what's BitTorrent. That's work, there is a special protocol for this application. It's called UTP or Micro TP, two names. And also, we work on packet contents modification on the, we consider that as actually as between layer 4 or 5, because we modify the UTP, but we have an application, it's called BitTorrent. So we developed a tool called BitStegNet that work with the BitTorrent application. Okay, next one. During our work, just for curiosity, we work on TCP just for as we said. Are we able to do something with the TCP? Yeah, we did. We developed something that's not main. That wasn't our concern. We developed something by Python, and we some data at the field, at the sequence number field, but that doesn't our concern. So let's summarize what we say now in the tools of what we did. As you can see, the tool is Timeshifter. The method is insertion. That's work at layer 3. And the protocol is ICMP. And the field actually, that's for the, we use the field, that data field at the ICMP packet. The second one is Stegnet. The steganography method is substitution work at layer 3 with protocol ICMP. And as you can see, it's the ICMP header data field. And the last one, and all our work was in this semester was with the last one, it's about the BitStegNet, that's work with substitution on layer 4 or plus, as we said, in Micro TP, and that's with we make substitution for information at the UTP header with a field called timestamp. Now my partner, he's gonna dig more in these subjects and do more explanation on this.
Hey, thanks, Sam. As Sam introduced to us, to you all, we utilized 3 tools throughout the course of our project, starting at Timeshifter, making our way through Stegnet and into BitStegNet here this last semester at a higher layer. What I'm going to explain further into is where it all started. We initially started with a proof of concept tool called Timeshifter, which, as Sam mentioned, modifies the delay of ICMP packets utilizing a library and utilizing NFQ to route those packets. Timeshifter was developed by someone named Infractuosity. It's what they go by as a name. And he defines it as Timeshifter modifies time delays of ping packets in order to send information between two terminals within the same computer. So we were using a virtual environment and had several terminals open in order to utilize this tool. If you look on one of the screens, this is an image that Infractuosity provided for how Timeshifter works. This is a real basic method of doing it. Pretty much in between packets, if there was a short delay between how those packets were pushed out, that would relate to as a 0. If there was a longer delay, that delay, a 1 would be received. And so those delays, there's a threshold. When that threshold's met and it exceeds that threshold, it pushes out a 1 bit. And that way we can modify the delay of these packets in order to generate a 0 or a 1 bit of how we see fit. From Timeshifter, we wanted to move forward with just modifying the timing of packets and delay and actually digging into how to modify the content of packets. We started with a real basic approach, just to more so as another proof of concept. Stegnet's a tool that we developed based off the entire theory and operation of Timeshifter, with minimal differences, just to work in a point-to-point environment. Instead, like I said, instead of delaying these packets, Stegnet modifies the content. It does this by capturing the packets from an NFQ, modifying its data field in these ICMP packets through the use of substitution, like Sam mentioned earlier. It would recalculate the checksum, and then it will push out those packets to its destination. Now, in order to route these packets properly, in order to receive them, we utilized rules through IP tables. If you look on the screen, the basic rule that we used was to accept all ICMP packets, output packets from the sending terminal, and give it a queue number of 0. And on the other end, the receiving terminal would have a queue number of 1 and receive all ICMP packets as an input rule. This rule would modify these captured packets on the sending terminal and release them to the network using that library, libnetfilterq, which we utilize through Ubuntu Linux as well. Here's a quick diagram of exactly how it works. So on the sending terminal, we would have 2 subsequent terminals open. One would be a ping that constantly is running, and the second would actually utilize Timeshifter or Stegnet to send that command. So once that happens, those packets from the ping push into the NFQ, and now the sending terminal on the other end, starts receiving those packets as they see fit and realize if they're 0s or 1s, and then pushes them out to the receiving computer, who on the other end receives it from their NFQ and their rules, and comes up with the message that was sent initially. Now, in order to make Stegnet work, there was a text file string that was utilized to pass. This is pretty much the covert information that we were trying to push through. So we directed the sending terminal to push a file name, and it would utilize this file name and push out the contents of that file as a string to the receiving computer. The thing about Stegnet was, as I initially started with, it was another proof of concept. It was very basic. We were utilizing a method that really wouldn't be any close to a standard at all. The ping packets, as we all know, could potentially never get through an active network often. It would be blocked. Additionally, that string that we were sending was sent as plain text. And if you were to look at those packets, you would start seeing that entire string right there. We didn't utilize any method of encryption. We really just wanted to see how the concept was utilized and how it would work. And lastly, that string that we could send was only limited to 48 bytes, 48 characters in general. Now, I'm going to introduce Manuel. He's going to dig deeper into the BitStegNet portion of the project.
Hi, everyone. First of all, talk about a little bit about BitTorrent Protocol. BitTorrent, as many of you may know, if not all, it's a file sharing protocol that It's peer-to-peer, so you don't need a server to transfer the files. It's why did we choose that to send the cover information? First of all, it's very common traffic over the internet. There are the connections are peer-to-peer. Also, it has highly customizable clients. We need to be able to set up the port number in order to be able to route packets appropriately. And also MicroTP, that's the protocol that's above UDP for BitTorrent, has appealing headers to input the cover information. Next, here we have the two alternate BitTorrent network stacks. The first of all, you can see this is the oldest one. It's TCP over IP. It was switched to MicroTP. That's over UDP because when you were uploading at higher speed, the router has a buffer that fills, and it interferes with the normal connections like web browsing or email. So that's why they developed MicroTP and over UDP. Here we can see the header fields of a MicroTP packet. We have type, version, extension, connection ID. Connection ID is random. It could be another possible place to hide information. There we have timestamp microseconds and timestamp difference microseconds. Those are the two header fields that will contain our hidden information. And you can also see that there's a window size to do flow control, sequence numbers, and also an acknowledge number. It looks similar to what TCP might look, but yeah, and we will focus on timestamp microseconds and timestamp difference microseconds. So first of all, we know the library we're using and our tool doesn't generate packets. It just captures them from a network and modifies them and sends them back. So we needed a program, a client that generates the torrent packets. So we chose BitTorrent because it's free, open, and multi-platform. And why this one? It's basically because it has MicroTP. We need MicroTP capabilities to perform the steganography. Also, it has a tracker mode. In torrent, you need a tracker. That's not like it's like a point on the internet that says where all the peers in a network are. So it has to be tracker. It has to have tracker mode, and also it has a customizable port number, as I said earlier, to be able to route the traffic correctly. So here is our lab setup. We set it up within VirtualBox everything. So just to test and that, we have two Ubuntu's connected in a subnet. Both of them are running BitTorrent, but one of them is running it as a tracker mode. It's both client and tracker at the same time. So BitStegNet. BitStegNet is our tool that we developed to modify BitTorrent MicroTP packet headers. So it follows the same structure as Timeshifter and Stegnet that we saw earlier, that diagram with the queues. The packet is generated instead of in a ping command, it's in a BitTorrent client. It goes to the queue. That's taken. That BitStegnet takes that packet from that queue. It modifies the timestamp, MicroTP timestamp. I'll show you later how, and it releases to the network. It has a capacity of around 1 bit of Staygo information per 100 kilobits of clean information. We consider clean information the file. I mean, torrent is a file sharing, so you have to have one clean file to share. So that's what we consider the clean information. Here's how the timestamp LSB substitution is done. It's done both LSB, the LSB of the letter that we want to send. It's the F right now. It's put in the LSB of the timestamp field of the MicroTP header. We can see the 0 that goes here. We didn't have to change it. The information was already there, so we just keep it. Here we have a 1. We have to change it this here, and another 1 and a 0. This is just the the last nibble of the letter F, but subsequent packets like packet 5, 6, 7, and 8 will continue will contain the other nibble, and then next packets will continue the next letter and so on. Here was dealing with BitTorrent traffic and the messing up micro TP timestamp field also messed up our connections. So we didn't know why, and we had to look into it, and we saw that the timestamp difference, that it might not look like a conflictive thing. It made without modifying the timestamp difference appropriately, the torrent traffic would not work. So we had to guess that as well. So here we have a flowchart. Flowchart, it's basically one, depends what bit do you want to send, the 0 or 1. If you want to send imagine we have a 1, then just check the timestamp LSB. It's the same of the bit we want to send. Just send it, and that's it. And if not, we have to subtract from the timestamp difference in order to make them match for the receiver part and the connection, and so the connection can be kept alive. If there are more bits, just go to the first part and do the same. So now Rob will talk about analysis in general.
So as Manuel mentioned, with BitTorrent, it's such a common packets. BitTorrent packets are very common to see across the wire. So looking at it from a Steg analysis point of view, about 3% of all network traffic is BitTorrent traffic at peak times. People are utilizing for file sharing of any type of files. It's gotten to be a very popular way of or a very popular protocol to utilize. So therefore, because it's so common, it's not considered suspicious or out of place. It looks normal. So if you were to look at if you were to sniff those packets, it'll only show up as BitTorrent or micro TP packets. So looking at it from that point of view, you're pushing out covert information that does not look like covert information at all. It looks completely legitimate, and that was a big kind of breath of fresh air for all of us when we saw that, hey, this isn't a complete waste of time and just digging into proof of concepts and theories. So in the timestamp field of those micro TP packets, additionally, what is also important is if you were really to look into the information of those packets, those microseconds, we're changing the least significant bit of the microseconds of that timestamp field. Therefore, generally, those very small fractions of seconds are nearly random. I mean, we consider it random. It's not really random because it is in a 0 through 9, but just how quickly they rotate and change out, it looks completely random, where you wouldn't be able to see any kind of fluctuation because that micro second field. Additionally, if you really wanted to approach it through a Steg analysis approach, only chosen Stego and known Stego attacks will work. Otherwise, it's just going to look like regular BitTorrent zeros and ones, and it shouldn't look suspicious at all. In order to kind of see the transmission, you would need to know where it started, where it ended. So if you wanted to see what information is being passed, you would need to find all of those packets in order to do so. So you can't just focus on one or a few packets at a time. You would need that whole portion to do so. So to finish up, analyzing what we did from starting at Timeshifter, going through Stegnet and into BitStegNet, some of our challenges were finding a way to modify moving packets instead of like a static file. As David introduced us, we can use the last one was JPEG, or I apologize if it was MP3 or something. Those are static files. They're there. Nothing's going to change in those files. All those zeros and all those ones inside the file are the same. What we needed to find a way to do was to capture packets that are constantly, going through the wire. Nothing's still. We have to catch them and change them and then release them. So we had this this dynamic approach to our packets that made kind of finding a way to insert covert information a little bit more difficult. We also had to satisfy all of our redundancy checks and all of our checksums for our packets prior to pushing them out initially during Timeshifter and Stegnet. Otherwise, they would return broken, and the integrity of our message wouldn't be good. Lastly, with ICMP packets, we mentioned how firewalls and or intrusion detection systems, ICMP packets usually will not make it through. They usually get blocked. We had to find a solution to find a way to, hey, let's find what kind of packets are normal, what kind of packets can we modify, and which type of packets will be utilized for a carrier. So on top of that, some of the limitations that were part of that, we only tested, as I know Manuel showed our lab setup there for BitStegNet. We tested in an isolated environment from start to end. We were really trying to attack our goal by just making sure it works, and to isolate that environment made it a lot easier, of course. Now, some future works, I'll point to that next on regarding the isolated environment. We could test on an active network. We're curious how it would work across the internet, but we don't think there would be too terrible of a change or from what we've tested, based on the fact that our packets, like I said, are very common and they're out there and they should be received at the recipient properly. Another limitation, we're only capable of sending text messages right now. We assume that we could send any type of file because deep down inside they are all just bytes. But we have only set up BitStegNet as a tool right now to pass on a text message. Lastly, I mentioned earlier that Ubuntu, we tested on Ubuntu because the library that we utilize for Timeshifter through Stegnet and into BitStegNet is only found on Linux. And that's the only reason we'd like to go, next slide, into a multi-platform sometimes. We'd like to test in open networks, and we would like that possibility to send any file if possible. Additionally, BitStegNet we find to be a big success. A future work could include creating a nice user interface, something a lot more user-friendly than just going through a shell script and things of that nature. So in summary, we started last fall utilizing Timeshifter to send a covert message by modifying the delay of ICMP packets from one terminal to another. We moved on to that, modified Timeshifter, and developed Stegnet in order to pass that same covert information between a point-to-point environment, no longer in the same station on terminals, by modifying the data field of these ICMP packets. And lastly, BitStegNet was our recent tool that we developed to send a covert message by modifying the timestamp and timestamp different fields of these micro TP packets. And Manuel we're going to show you a demonstration of exactly how BitStegNet works. Naturally, you're going to have to see this from both the sending side and the receiving side. While there may be a delay here, we're going to show you, anticipate how these terminals are almost working at the same time. And Manuel explained that further, exactly how that works.
Okay, so we see BitStegNet running in transmitter mode. We set up the message. Well, we set up a message that you will see. Also, we have the BitTorrent program running in the right. So the way to go is we have the torrent in the receiving part. It's resumed. It's stalled, waiting for transmission to start. Notice that here in the sending part we have you cannot see it very clear, but the torrent it's done. It's 100% complete, so it's just saving information. So right now, we just click resume, and the traffic starts. This is this is real time. This is a video, but it was done real time. That's the speed we get. Remember that we are in a virtual environment, so everything is done within the same hard drive, so that's why it goes so fast. So here we have the receiving part. Imagine it running at the same time as the other video. We have the torrent that we've been testing on. It's not at 100%. It still has some percentage left. It's paused, and we first resume this torrent. Right now it's stalled. It's the state when we had in the first video the torrent stalled in this part. We had to go to the transmitter, resume it, and then the transmission will start. This is the receiver computer, and there you go. This is done in a video, but we will show you this live and after, so you can test with the message and all that.
So as he was mentioning, we will show you this demonstration in real time. We can show it to you live upstairs later after lunch. Additionally, we can explain further exactly how we utilize these protocols and utilize these tools in order to pass this covert information. So at that time, we're open to any questions if you have any. Yes, sir.
Two-part question. You said the limitation currently was just text messages or text output of some sort. Is there a specific size of that message, or could it just? Do you remember
that? So as I said earlier, right now the size of the message depends on the size of the file that you have to transfer the clean file.
Okay.
So if you have this file here, it's 1.9 megabytes, and it can send up to 180 bits. So its character is 8 bits, so it's more or less 1 bit per 100 kilobit, more or less.
Okay, so 100 to 1. Okay.
No, it's
1,000 to 1 ratio?
No, it's like 100,000 to 1.
Okay. All right. So you could. All right. That's cool. And now with file sizes being so huge, and what BitTorrent is normally known for, transmitting large amounts of data, could you theoretically then encode a binary file to send it in plain text, receive it on the other end, and then decode it?
That's a future world we're thinking of. It's possible to be done. We're just now embedding the bits into the LSB. So whatever you do with the bits and the receiving part, I mean, you have them, so you can do whatever you like. So it's possible, yeah.
In theory, absolutely. Yeah. Right. Thank you. Sure. Yes, ma'am.
Can the person's IP address affect how fast the packets, how fast the programs pick up, how fast or short they get
trackers?
Yeah, trackers.
Yeah, that's a really good question. That needs to be tested in an open environment, because right now it's just 2 IPs that we knew. But yeah, the thing is, in the torrent file that it's open in both clients, you got the IP of the tracker, and that tracker is the one that communicates the IP addresses to both clients. So we don't really know how will that affect, but I don't think it will affect that much. It's just a communication of the IP address, and when they got the IP address, it's just a point-to-point communication, so you don't need to go through a tracker anymore.
Yeah, that tracker already knows. Excuse me. That tracker already knows those IP addresses. The point of the tracker is to almost act like a map for any other client to utilize. Hey, this is the IP addresses. These are the addresses of the clients that have the file that you're sharing and whatnot. So, yes, we would have loved to test it in an open environment. We haven't had the chance to do so. Yes, sir.
What's the largest file you've tried to send across in terms of size?
No, yeah, it was. We only tested. I mean, we don't test it. I tried to. I had what I thought it was a small file. And I don't remember how it went, but it was like a couple of kilobytes. And I tried to create a big file, but I came up with this 1.9 megabytes file that that's what we've been using. We have not tried doing it with a big video file, for instance, or any of that. We have not tried with a huge message in a video file, for instance.
Right, because I would wonder if there's a failure after a file of a certain size tries to get transmitted.
It shouldn't be any failure because traffic, it's going to be, I mean, everything is the same. The file, if the file is 1 kilobyte to 1 gigabyte, or I think traffic is always the same. You just divide the file by chunks and send those packets, like BitTorrent packets, to the client. So instead of having, remember that this one is 1 bit per packet. So instead of having 180 packets like we have with this file, you could have, well, X packets, and the number the file is divided into.
Because there is a delay between the send and the receive, right?
No, it's almost, in an open network, it's good because the delay you will have from when the transmitter sends you the packet from, imagine clean torrenting, right? You get the packet from another peer, so it would be the delay between that peer and your computer. It's not, there's a little bit of delay. You have to take the packet and change the LSB, and that's it. But that's really fast. Thank you very much.
Yes, sir.
So it's using UDP, so there's sequence numbers in that, so that if things come out of order, that doesn't...
Yeah, that's right. The thing is, it's using UDP, so we take, Micro TP has that sequence number, so if they came out of order, that's another thing we wanted to test, but we didn't have it. It's fewer work, as I said. If they came out of order, you have the sequence number to reorder them at destination, but you have to do it manually because you capture the packet before the Micro TP header is interpreted at the destination. So the BitTorrent client does that for you, but then you don't have the packet anymore because it's already been processed. So you'll have to read the sequence number, compare it to the previous one, or put in a buffer or something like that, and then you'll have your order message at the receiving part. Thank you for your question.
Does anyone have any other questions? We're nearing the end of the time anyway. Hey, thanks so much for giving us the opportunity to speak with you today.